we talked about the domain and codomain and the range, and we tried to, find the difference between them. And I threw out an example, just kind of off the top of my head, but if I really thought about it, this is probably a better example to look at as a regular transformation. And then we'll see that when we study linear, when we put the word linear in front of transformation, this is an example of something that is not a linear transformation. And so we'll stick to linear transformations once we start defining that. But I wanted to go over this particular example because I think it's interesting, and it could be pertinent for people might have seen this before if you've taken Calc 3. And so the idea is to establish some sort of relationship between the abstract notation that we're using versus a concrete example. So in this case, t, we want to know what kind of function this is, or what kind of transformation this is, and we want to know essentially the domain and the codomain of this thing. So what is the domain of this transformation? What's the codomain? Any ideas? Any thoughts? You guys know what I'm talking about? Yeah, it goes from R2 to R2. It goes something from 2 dimensions to something else in 2 dimensions. So t goes from R2 to R2. And this particular transformation takes a certain set of values, and then it brings it to a certain set of values, and it takes it to R2. So what we could do is find some sort of some examples of which numbers go to what, and then try to see how the graph might look like. Question? I don't know. Who said R2 to R2? How did you know? So it has 2 entries. That means you put something that's 2-dimensional in there, and the output looks like it's a 2-dimensional vector. So, okay. All right, goes from R2 to R2. And so to try to get an idea of what this thing might look like, we still have a chance of visualizing this because R2 and R2 are things that we can visualize. So let's see if we can try to get an idea of what this thing might look like. And we can do the primitive plug in numbers and see what you get kind of thing, where we put in a point, or I guess we should put in a vector. Where we put in an r and theta value, and then we'll get an r and r cosine theta and r sine theta value out of that. So this kind of gives some numerical ideas of different kinds of images. And so, the easiest one is to put 0, 0 in there. And what happens when you get 0, 0 is that you get something, well, that's pretty boring. You just get 0, 0. So let's put something a little bit more interesting, like let's let r equal to 1 and let theta equal to 0. So if r is equal to 1 and theta is equal to 0, what's my output going to be? 1, 0 again? Now, theta is going to go into the sine and cosine. So if I want to start putting in more points that have different theta values, I probably want to use, you know, the nice values for theta. So let's say we put 1 in for r, and let's maybe put pi over 4 in for theta. What do you think we're going to get? Root 2 over 2 and root 2 over 2. You guys remember your trig, huh? Unit circle and all that stuff. Okay. Well, that's a general idea of trying to figure out, actually, unless you really put in a whole bunch of numbers, this numerical technique is not going to help us visualize things that clearly. And so if you have a computer and you can try to plug in a bunch of numbers and see what your outputs are, that might be a better way to do it. Or even better is try to get a visual of it after you get your outputs, try to plot your outputs. Now in 2 dimensions, we can think about this as something going from the xy plane to another xy plane. And sometimes in this particular example, since the xy inputs are actually labeled r and theta, we would normally call it an r theta plane, and then here maybe call this an xy plane. And then we can say that x is equal to the first component of the output. What's the first component of the output? Oh, not numbers, but according to the formula, r cosine theta. And then we'll let y equal to the other one. Okay? If it hadn't looked familiar before, for those people who have taken Calc 3, you should already know what this is. What is this? It's a polar coordinate transformation. Okay? And so we can plot points, lots and lots of points, and maybe plot regions to see how regions would look like if we had regions there. I don't know. Well, let's take a look. We have to kind of call it XY, so let's take a look at, instead of points, since it's really hard to look at just points, let's look at a specific region. And the region that I'm going to look at is, let's just say from 0 to 1 square. And then I want to see how this transforms. Now I have to pretend that this is r and theta on the domain side. And so I'm going to go to the range side. And if I were to plot this, I could try to see where some of these points go. If I let my r on the left side go from 0 to 1 and my theta on the left side go from 0 to 1, I'm going to transform this into something like this. Now, if you think about it carefully, when r is equal to 0 on the left side, what points are described when I say r is equal to 0 on the left side? In other words, if this is r and theta, what happens when r is equal to 0 here? It's what? Not quite what I was getting at. Let me do it this way. R in this case is x. So if I were to graph this, what's the graph of this going to look like? Somebody goes like this, it goes like that. It's a vertical line, right? Not a horizontal line. So this is a vertical line. So what happens when R is equal to 0 here for both of these? Zeros, right? It doesn't matter what y is equal to. When R is equal to 0, maybe y could be pi over 4 or pi over 7 or negative 23. It doesn't matter. R is 0 means that this whole thing, this is going to be 0, 0. So what happens is that this whole line collapses into one point over here that you can't see. I suppose if I take out the, I don't know if you can see if I take, oh, there it goes. See that little dot? So that whole thing collapses into there. So now if I let this grow a little bit, Now let's go back to our original graph that we had where we had a square. So what we can do is we can imagine that these points, when R is equal to 0 over here, all get mapped into here. And then as we let our R, our x value, our value go wider and wider, this is going to get wider and wider. So we can kind of see that if I introduce a slider and change our y, our x values, our r values. Just go from 0 to 3, for example. Hi there. So in this transformation, it looks like the x or the r value kind of controls, if it goes to polar coordinates, it kind of controls the radius of things, right? All right, now let's see what happens to our theta value if we change our theta values. So our theta values, let's put a slider on this also. And pi, 2 pi, 6 point something, let's go to 10. So we can put the axes back, x and y axis, and see how that would look like. Actually, let's take this out because it's going to make the other graph look a little confusing. But if I change, the b will control the theta values. It's going to go from 0 to whatever b is. And if you let b go to, uh-oh, I think we stopped somewhere here. Weird things are happening now. This is about to crash. Anyways, you get the idea. This particular transformation transforms r theta values into xy values, and then it finds a relationship between circles and rectangles. And that kind of stuff is useful when we're working with things like multiple integrals and stuff like that in Calculus 3. All right. So in this class, we're really not going to be working with those types of transformations, but I thought this was an interesting transformation to look at. So let's move on to where we eventually want to go. Oh, yeah. Yes. So these transformations, when they go from, when we plot our regular functions, our functions that go from R to R, we can plot one R as your X value and one R as your Y value. When you look at a transformation that goes from R2 to R2, you think about the 2 dimensions that you have to plot for the domain and the 2 dimensions you have to plot for the range, and that becomes 4 dimensions, which we can no longer picture. So the true graph of that is something that we're not going to be able to see. But if we take it apart and say, oh, this is 2-dimensional and this is 2-dimensional, and plot those separately and just draw arrows to go from one to the other, then we can still visualize it. Yeah.
So those aren't really 2 graphs. Those are actually 1 graph.
Yeah. So let me say that. Let me continue drawing on this and say, for example, when R goes from 1 to pi over 4, for example, this gets mapped into, what does this get gets mapped onto? Quarter? I think I know what you mean, but you mean up to here, right? Actually, even better. The interesting thing to look at is what happens to our I don't know what we would call it. We would call it our our grid. So we can think about this as having a grid in Cartesian coordinates that would look like that, and then this would have a grid that would look like that. So in fact, that picture over here, if we take these graphs out and just look at the grid and see what happens to the grid. So technically, this grid goes on forever. Oh. Yeah, I should just show you my computer. So the idea is that the horizontal and vertical lines here turn out to be, well, the horizontal, is this horizontal? The horizontal lines, the vertical lines here actually turn out to be circles, concentric circles. And the horizontal lines here turn out to be rays coming from the origin in a lot of different directions. So somebody wants to come over here and look at this because this is all screwed up and IT people are not coming to fix it. All right, so that's the idea. So this is our representation for a linear transformation. We'll call that a mapping from T, or from R2 to R2. And then if we take a look at the domain and range by looking at something here on the domain side, and then the image of whatever that is on the range side, then that's how we can visualize these linear transformations. All right, so let's take a look at a matrix transformation. A matrix transformation is essentially a linear transformation. I've been saying linear, I haven't fully defined linear yet. But a matrix transformation is a transformation that uses a matrix as its function. Okay, so in this previous example, we have T of X, and then the output is going to be whatever matrix we have. Not a matrix, but a vector, whatever vector we have. So this is a vector in R2 that goes to another vector in R2. So we say that this transformation goes from R2 to R2. But a matrix essentially does the same thing. And so a matrix can be seen as a transformation where you multiply a matrix multiplication, you take that matrix and multiply it by an appropriate sized X matrix or vector. An appropriate sized vector so that the matrix multiplication would work. So here I have this example. I wanted to write this out, but I guess it's all typed out already, where I have a matrix A, and this matrix is a what by what matrix? 2 rows, 3 columns. It's a 2 by 3 matrix. And so if I find an appropriate vector, variable X vector, to multiply it by, then I'm going to get an output, which is another vector. So our matrix A is a 2 by 3 and then X, the X vector here has to match. If I want this to be a vector, I want it to be a column vector, and so it has to match with this number of what in A? Number of columns in A. So there's 3 columns, so this has to be a 3 vector. And then what you're going to get is an output. We can call it B, but a lot of times people just call it Y, like Y equals A of X or F of X. So the Y vector is going to be, if you get rid of the 3's here, it's going to be a 2 by 1. Okay, so we can say that, okay, this matrix idea can make sense now. We can have a matrix transformation. And that means we're putting in a vector. So this A transformation, which we can rewrite back into T again, but this transformation takes R what to R what? R what? R2 or 3? What's the output? Output is 2 vector, right? So the output, this is your output. This is your Y vector output, and there's 2 components. So this goes from R2 to R3. So look at the way the transformation is written, going from R what to R what, and then look at the dimensions of the matrix. Make that connection now. It's always going to be like that. Oh, I guess this should have been backwards, huh? It should be R3. R3 to R2. Is that right? Okay, now look. And remember, make the connection between the functions going from R something to R something and the size of the matrix. So they say if you have an M by N matrix, then your transformation is going to go from R what to R what? N to M. Okay? That's how the transformation is going to work. Yes?
Why that one is archery, but it has two entries, like it has two rows, but it has three columns. So the column is going to be the R3 because of, like it has four columns, it's what's going to be R4.
Yes. Because otherwise, if you put an R3 vector there, it's not going to work, right? So in this case, we need an R3 because we have three columns. So that's the number of columns will set the dimension of the domain, and the number of rows will set the dimension of the range, or codomain. Okay? Yes?
The dimension, but the number of columns on the right hand side determining the dimension.
Yeah, the right side is one column.
Yeah, the right. Yeah, so this don't be tricked by this matrix over here or this vector. This is actually just a vector with one element in the numerator, one element in the first component, one element in the second component. So this is really a 2 by 1. This is only one column. When you put in the values for x1, x2, and x3, you're just going to get numbers. Okay? Is that what you're referring to?
Okay.
Yeah. So there are no commas or no spaces. It's you're adding things in there. And you see how that works, right? The matrix multiplication got me that. Any questions? All right. So now that we have introduced this idea of a matrix transformation, the matrix transformation is related to a transformation, a regular transformation, via this idea of a linear transformation. So the definition of a linear transformation is going to be the important part of this class. I mean, this is, after all, linear algebra. And what we want to say about this is that if you have a linear transformation, then you can write your transformation as a matrix. If you have a matrix transformation, then that is a linear transformation. Okay, so the backwards part of it, if you have a regular transformation that is not a linear transformation, then you cannot write it as a matrix. So the matrix transformation will only work for linear transformations. And now that we have this down here, let's make a note. Let's make a note that our polar coordinate transformation that we saw earlier is not a linear transformation. Okay. So there's some special geometric features and other important things that go with a linear transformation, and not all transformations are linear. For example, the polar coordinate transformation is not linear. So what is a linear transformation? A linear transformation satisfies two things, and one of them is called, what's it called? What? No, it wouldn't have anything to do with the domain or range. It's called addition. What's the technical term? Additive property. It's not quite distributive. It's not distributive. Is not. This is not distributive. No. Closed under addition. I don't think that's it either. The closed under addition is a property that we'll look at when we take a look at vector spaces. So let's just say it satisfies this property. When you add two vectors in the domain and then apply the transformation, it's actually equal to the sum of those outputs in the codomain, in the range. So let's call that an additive property, and then the other property is a scalar multiplication property, where you scale something in the domain. Is the same thing as taking the transformation and then scaling in the codomain. I don't know if I call it vector addition. I'll find a name for it. Do these properties look familiar? Where might you have used these properties before? You have used these properties before. Where might you have used these properties before? What in calculus did you use these properties? I mean, what is in calculus? The integrals. Yeah, so the integrals, if you have a polynomial, you can break that polynomial up and take the integral of each one separately. I mean, we don't think about it that way anymore, but when it was first introduced, it was this property. It was this first property that told us that we can break it up into separate integrals. And also, if you have that polynomial with a coefficient in front, we can take that constant out, right? So taking that constant out is like this scalar multiple property. We also did it for derivatives. So it turns out that integrals and derivatives are linear transformations as well. So these two properties over here are what defines a linear transformation. The other two properties just kind of follow as a result of the first two properties. And this says that a transformation always takes your zero vector to another zero vector. So a vector in your domain, the zero vector in your domain is always going to get mapped to the zero vector in your range, in your codomain. And then a multiple addition and scalar multiplication can extend to as many terms as we want. Okay. So what we could do is we can show that this polar coordinate transformation is not a linear transformation, right? It should not work on these things. So let's give it a try. So according to this, we have T of UV. So actually, let me get this straightened out first. Let's let u equal to r1 and r2, or I'm sorry, r1 and theta 1, and let v equal to r2 and theta 2. And what we want to show is that if this is in fact a linear transformation, we want to show that the first property is going to work for us. So let's try that. U plus v is what we need to put inside of the transformation. So what is u plus v? We would add those two vectors, r1 plus r2, theta 1 plus theta 2. And so this is a vector in R2, right? It's a 2 by 1 matrix. 2 by 1 matrix. And so let's put it through this transformation. T of u plus v is equal to T of R1 plus R2, and then theta 1 plus theta 2. Okay. So we're going to put R1 plus R2 in for R. So according to this transformation, this is supposed to equal to R1 plus R2 cosine of theta 1 plus theta 2, R1 plus R2 times sine of theta 1 plus theta 2. Now what I want is to eventually get this to look like R1 cosine theta 1, R2, R1 sine theta 1 plus R2 cosine theta 2, R2 sine theta 2. So I eventually want to get there if this was supposed to be a linear transformation. And the thing is, I don't know if I can fiddle around with these trig functions enough to make it look like that. Yeah. It's not a multiplication. T is just a symbol that says, it's like saying f of x. So it's like saying f of x and say f is applied to x. And then you remember this? F of x plus h minus f of x all over h. So it's like putting in those things in there and then seeing what you get. So the point is that I don't think this is a linear transformation because there's no way to get from this step to this step. I can distribute the cosine and the sine. It looks like I can distribute that, but then I don't think any of the formulas for the cosine or the sine of the sum of two angles will generate anything that would give me this. So no way to get result. So then we can conclude that it's not linear. Okay. Now let's take a look at this example. Which I said was linear. And let's see if that works out. So by the way, the first one didn't work. So the second one, T of C times U. This, we don't need to look at this anymore, but if you were to try this out, you'll see that this also will not work. Okay. will also not equal to c times t of u. All right, let's go back and see if we can do that problem. Which we said was a linear transformation, and then we'll show that, actually, let me get rid of this matrix business and just say, what if we're just looking at that and say this is a linear transformation? So let's prove that this is a linear transformation. Let's go through the proof of the linear transformation, and we need to show two things, remember? So we need to show that the sum and the scalar multiples properties are going to work. So the first part says that let's first determine our u's and v's. Let's let u equal to x1, y1, and let's let v equal to x2, y2. Wait, we need 3. Sorry. x1, y1, z1, and x2, y2, z2. If you choose a number, the numbers might make it so that it's a special case, and so we want to get rid of the special case and go to the most general way to approach it. So t, we need to figure out what u plus v is equal to. x1 plus x2, y1 plus y2, z1 plus z2. So t of uv, u plus v, t of x1 plus x2, y1 plus y2, z1 plus z2. And this is equal to, according to this output, it's going to equal to 5 times the first variable, which is x1 plus x2, right? Minus 2 times the second variable, y1 plus y2, plus 3 times the third variable, z1 plus z2. What? And then for the second component, it's going to be x2, which is y1 plus y2, plus 4 times the third component, which is z1 plus z2. And so from here, it's just a bunch of algebra to make it look like what we need to make it look like. Do you guys know what to make it look like? You know our goal here? When you're proving stuff, it's always nice to know what your goal is. So your goal is to make it look like TU plus TV, which is basically this thing plus, well, that thing. So let's multiply the 5s and the negative 2s and the 3s and then separate it. So I'm going to do a couple of steps here. 5x1 minus 2y2 y1 plus 3z1 plus 5x2 minus 2y2 plus 3z2. y1 plus 4z1 plus y2 plus 4z2. So I wanted to separate it because these are the two two pieces. I'm going to split this up to two matrices or two vectors now. So this is going to equal to the vector 5x1 minus 2y1 plus 3z1 and y1 plus 4z1 plus, and then 5x2 minus 2y2 plus 3z2, y2 plus 4z2. And then this is going to equal the t of x1, y1, z1 plus t of x2, y2, z2, which is equal to t of u plus t v. All right. So that's how you would prove the first part of this thing being linear. Are there any questions? I know there's a lot of subscripts going on here and the variables, but if you can work through that, then this is a view of a proof that you would normally do in a linear algebra class. So that's the first part. The next part is we want to know what happens some weird things happening now. We want to see what happens when we scale the vector. So scaling the vector, it's like saying c x1, c x2, c, oops, y1, y2, and y3, z3. Ah, getting confused. So scaling says that you're going to multiply all the components by that constant, by that scalar. And so let's put that into our transformation. So this is going to be 5 times c x1 minus 2 times c x2 y1, sorry, plus 3 times c z1. And then the second component is y1, c times y1 plus 4 times c times z1. So all of these have c's in them, and all the terms, you can factor that out, right? So we can factor out a c from the top, we can factor out a c from the bottom, or not the top, but the first component, we'll factor out a c from the second component, and then we'll eventually factor a c out of the whole thing, but let's rewrite everything over again. 5x1 minus 2y1 plus 3z1, and this is y1 plus 4z1. So if you take the c out, we see that this is exactly c times t of the vector. So the string of equalities here will lead us from the first thing that we want, where we multiply the vector in a domain by a scalar, and then that's the same thing as taking your transformation vector and then multiplying that by the scalar. Okay? So this is an example of proving that something's a linear transformation. You should probably expect this on the test since we're spending a lot of time on it. Okay. Any questions? All right. The bottom line is that if you have your variables and you're not taking your variables to any powers or taking them to sine or cosine or any weird thing like that, logarithms, exponentials, then you're probably going to be a linear transformation. Also, you have to make sure you're not adding any constants. All right. So like I've mentioned, the main part of this discussion is that a matrix multiplication is a linear transformation. So that's why linear algebra, when we're talking about linear stuff, we're always looking at it in a matrix point of view, is because whenever we have a linear transformation, we can always look at it as a matrix. And that's why the study of matrix is really important in linear algebra, because we're dealing with linear transformations and linear things, and the matrices are the best way to try to describe or try to work with these linear things that we're working with. All right, any questions? Yeah. Well, I think we said it here that AX can be seen as a transformation where it's the matrix times the vector. And so that's the relationship. That's the key that we want you to be able to link up. Okay. Oh, instead of twos here? Yeah. They're all supposed to be ones. All right. So addition and scalar multiplication and linear transformations. So let's take a look at a handful of common linear transformations from R2 to R2. R2. Let's change this. So R2 to R2 is it's easy enough to be able to picture. And so I'll just list down a bunch of examples and show you how they look like in the graph, just so you can try to visualize what they are. So there are transformations called projection transformations, shear transformations. They call it contraction dilation, but you can think about it as expanding, compressing, and then rotation transformations. So the first type of transformations, projection transformations. And can you imagine what happens to this if you think about this as a transformation going from R2 to R2? Let's see what happens. So remember, the thing to do is to try to visualize this. You either use a graphing program or plot on some basic points. or general points and see what happens. So I think this one we can kind of view. We can use x1, x2, or you can use xy. I think let's use xy so that we can assimilate our thoughts back to the xy plane. And if you apply this transformation, ax 1, 0, 0, 0, what happens to this? What happens when you do this matrix multiplication? So it's a 2 by 2 with a 2 by 1. So when you make this multiplication, it should be a 2 by 1. And how is that 2 by 1 matrix going to look like? What's in the first component? Just x, right? It's x times 1 plus 0 times y. And what's in the second one? 0. So it looks like whatever we do, whatever values we put in for x and y, it's always going to drop the y value and make it 0. And the x will remain the same, right? So imagine how that's going to look like. Maybe plotting some points initially and then try to generalize things. So like a 0, 0 would go to 0, 0. Okay. It is a linear transformation after all, so we know that's always going to go there. What happens to the point 0, 1? It's going to go to 0, 0 again. What happens to the point 0, negative 2? It's going to go to 0 again. What happens to the point 1, 0? It's going to go to 1, 0, right? So it looks like what happens here is that all these things are going to get collapsed into the x-axis, right? So for example, if you restrict your domain like we've done, if you restrict your domain to like a square over here, what's going to be your output? A line, and a line segment from 0 to 1 on the x-axis. Does that make sense? That's easy to view, yeah? No? Oh, yeah. Yeah, so we could do a projection from R3 to R2 where your domain would be points in R3 and then your R2 would just be the XY plane, the YZ plane, or whatever. Not quite, no. Yeah, particular solution, you select one of the families of curves. Anyways, differential equation talk. All right, the next one is a shear transformation. And this one, let's try to imagine what's going to happen here. Let's take AX again, where X is just XY. And so what's going to happen to your outputs? So what's the first component in your outputs? X plus K times Y. And then just Y. Okay, so it looks like the points that you're dealing, when I say points, by the way, you know, it's like saying vectors. So whatever point we choose, it looks like the Y is going to remain the same, but your X will change depending on what K is. k is positive, you're going to have x plus some scalar of y. So can you imagine how this thing might look like? Let's let k be positive 1, for example. And then let's take a look at some points. First of all, 0, 0 is going to be 0, 0. What happens to the point 0, 1 when you put x is 0 and y is equal to 1? It'll be what? It'll be 1, 1. So now you've already kind of moved over here. Let's put this point 1, 0. Where's 1, 0 go? It stays at 1, 0, right? And then where's the point 1, 1 go? 2, 1. So another neat thing about linear transformations is that it maps lines into lines, it maps parallelograms into parallelograms. So you can kind of see that this actually, if you take a look at this line segment, it would correspond to this line segment. And then that's what happens to this transformation. Okay? And if k is negative, then it's probably going to go the other way. If k was larger, it's going to shear larger. Contraction dilation, can you imagine what this is going to do? Well, to help us imagine, maybe we could just take a look at what happens to x, y values. So just kx and ky. So it looks like your points are going to double. If we take a look at it as vectors, it's going to get scaled by that vector going outward. And then this is the one that's really kind of interesting. Is this even a linear transformation? How can you convince somebody at the STEM center is walking by and says, this is a linear transformation, and you're going to say yes because?
The function of the variables that we're using, x and y, not a function.
The function, yeah, that's part of it. X and the y's don't go as sines and cosines. What's theta? Arbitrary. So for this to actually work, we want to set a value for theta. And one more question. How do you know this is a linear transformation? If theta was fixed, then this is a linear transformation. Why? Because what? If theta is a constant, but why is it a linear transformation? Because it is in a...
Well, I was going to say, because sine theta, if theta is constant, then that will just turn into a constant, and it's basically like any number in front of it. Just a coefficient.
Just a coefficient. Yeah, so sine. So these things inside of this thing is just going to be numbers, but this thing, the thing is a matrix. And if you have a matrix, that's as good as a linear transformation. All right, let's take a look at some pictures. 1001 is called the identity matrix. And so if you map anything with the identity matrix, it's like multiplying by 1. We'll see that next chapter, in chapter 2, when we start talking about matrix algebra. But now let's take a look at the projection. You can't see it. What if we clear this out? You still can't see it. It's so thin that you can't see it. It's there. It should be a line. So that didn't work. Let's do the shear. Shear transformation. Actually, this would be funner if this was animated. So let's animate it. Well, that's this axis over here is actually this axis. And my computer is all right. What's the other one? The expansion, or what's it called? Contraction. This might be weird. So those are positive values. If I go to negative values, it goes on the other side, right? And then the last one, cosine A, what is it? Negative sine A, sine? Positive. So this one might be more interesting if we go from like 0 to 3, 6, 7. So it's a rotation transformation that rotates whatever object you have. Okay? So we got some cool pictures. You got some ideas of what a linear transformation does. We've seen one proof of showing something is a linear transformation and one proof that shows something is not a linear transformation. Okay, so there might be a few more things that we need to discuss in terms of linear transformations, but next time we meet, we're going to go straight into, well, I guess we have to talk about the standard matrix and stuff, but after we do this, we're going to go into 2.1. All right, see you guys.